Hello, I'm Hugh Manfield, and welcome back to the Fluid Space Theory channel. Now, everything in my videos and the 10 core lectures is included in my book, Einstein and Aliens. The first half of the book is a science fiction adventure where you learn about fluid space theory by following Ricky on her adventures through the galaxy as she meets a variety of alien species. And the second half of the book is a set of appendices where all of fluid space theory is laid out in the reasoning and the math. Now, last week we were talking about cosmology, and there were a few things about this fluid space theory cosmology that I couldn't fit into that lecture. So I decided to make a part 2. Now, the thing about fluid space theory cosmology is that it's a much messier place than the standard model cosmology. Fluid space theory tells us that antimatter would have collected into the blue regions shown in the cosmic microwave background, while matter collected into the orange regions. And there would be this amalgamation of regions of matter and antimatter, and they would each be doing different things. So if we think back to the very early universe where matter and antimatter had just recently condensed out of the primordial energy field, instead of a period of annihilation, there would have been a period of segregation where antimatter would tend to collect in various pockets and matter would collect in other areas. And between these areas there would be sheets, boundary layers where particles would still be annihilating, and that would create a photon sheet basically that would tend to push the rest of the matter away from the barrier, and eventually the universe would settle into a stable system of matter and antimatter. And I call it the cosmic cheese theory because the early universe would have looked like a block of Colby Jack cheese, where you might have antimatter represented in the white areas and matter represented in the orange areas, and there would be an equal volume of each. So if you cut a chunk out of the cosmos, it would look a lot like a slice of Colby Jack cheese. And you're not going to be able to eat Colby Jack cheese anymore without thinking of the cosmos after you watch this video. And I think that's a good thing. So here we see a representation of a video that was put out by the University of Chicago, and it shows how from the early universe to the present that the large scale structure formed. And you see it starts out like our loaf of Colby Jack cheese, and it evolves into what we see more or less today with the galaxies and galaxy clusters strung out in large filament structures. And I'm sure they created this using a lot of dark matter and dark energy in their model, but it would work the same way if you used expanding space-time for the areas occupied by antimatter and contracting space-time for the areas occupied by matter. The antimatter would tend to disperse, creating voids, and the matter would tend to collect and contract down into clusters and filaments, and the result would be very much the same. So there's another way of looking at the cosmos to try and get some answers, and it's called the anthropic principle. Basically, the anthropic principle says we see the universe the way it is because if it was any different, we wouldn't be here to see it. Now that may sound like circular reasoning, but it actually sheds some light on certain issues. What it means is that if a cosmos expands too quickly or collapses too quickly or doesn't exist long enough, there won't be enough time for intelligent observers to evolve or develop. And so no one will be in that cosmos to witness it, and it will go unseen. So we live in a cosmos where enough time has passed that we have come into being as intelligent observers, and possibly many, many more out there somewhere in the cosmos are also observing. But it takes a certain amount of time for that to happen. And then after that point in time, intelligent beings can arise randomly as the universe progresses. Well, with the current model of universal expansion, the galaxies are moving farther and farther apart all the time, and it's also accelerating. So what this predicts for the future is that instead of looking out and seeing a galaxy-rich cosmos that we do, I mean, we look out there and we see galaxies as far as the eye can see by the billions. But for intelligent observers in the future, they may not see that many galaxies. They may see only a handful of galaxies, or they may only see their own galaxy existing in an isolated void. So that means that we're lucky to be living in the time period where we are, where we see a galaxy-rich cosmos. And that the odds are, if we landed randomly sometime in the future of the universe, where intelligent beings are allowed, we would not see a galaxy-rich cosmos. So the odds are against us seeing what we see, according to the anthropic principle, when applied to the current standard model. But if we take this fluid space theory model, it's an expansion that doesn't involve galaxies moving farther apart. As the vacuum energy decreases, the length contraction goes away, the universe expands, but the galaxies, the distance between the galaxies for residents within the cosmos, just like passengers on the space train, does not increase. So the real point is that instead of looking at Hubble expansion, where the space increases between the galaxies, that's kind of like looking at the cosmos from the outside point of view. But there's no way we can do that because we're living inside the cosmos. We can't look at it from the outside point of view. So the fluid space theory cosmology is an expansion that doesn't include galaxies getting farther apart. And what this means is that as we look out, no matter where we are in the future, we're going to see a galaxy-rich cosmos, which then means that fluid space theory is not at odds with the anthropic principle. The other thing that fluid space theory answers is the arrow of time. When we go about our daily lives, we see irreversible processes. We scramble eggs. We don't see eggs unscramble. We stir coffee creamer into coffee. We don't see coffee creamer becoming unstirred. These are forward-moving processes that unfold in forward-moving time. And we don't see processes unfolding backward, even though our equations work perfectly well for forward-moving time or backward-moving time. So what does fluid space theory say about the arrow of time? Well, if we put ourselves at the very beginning, the universe is a single, ultimately dense, infinitely length contracted, infinitely time dilated region of space. Sometimes it's been called the primordial atom. Now let's say that the primordial atom is at the tipping point. It's ready to go and the universe is ready to unfold. But does it tip forward in time or does it tip backward in time? Well, for fluid space theory, it doesn't matter. If it tips forward in time, the universe will unfold, antimatter and matter will condense out, and then matter will contract into stars and galaxies, and we'll see the cosmos the way we see it, with antimatter dispersing into the voids between the galaxy clusters. So what if the universe decides to unfold backwards in time? Well, that means the antimatter, moving backward in time, will take up the role that normal matter takes up, and that matter, moving backward in time, will take up the role that antimatter takes up. So we'll see a cosmos that moves backward in time will have antimatter condensing down into stars and galaxies, moving backwards in time, while normal matter, moving backwards in time, expands out into the spaces between the galaxy clusters. So what this means is that no matter which direction the arrow of time decides to go, we'll see the same kind of cosmos that we're looking at. So we may actually be moving backwards in time in an antimatter universe, and there's no way to really tell. So in conclusion, there's no need anymore to eat the dark matter, dark energy sandwich. There's something better, and it's called fluid space theory. And It explains the cosmos in a way that is much more easily understood, in a way that you don't have to use a lot of fancy, indecipherable physics speak, and it's within the reach of just about everybody on the planet. So hopefully you'll like this video and help spread the word. Until next time, I'm Hugh Manfield.